Good day, everyone. I'm Marjan, presenting the novel methodology to assess MRT on behalf of a group of researchers from PJ Carey Consulting and Penn State University. This methodology shows a unified approach to assess the mean radiant temperature, MRT, in a single process, even in a very complex outdoor space. It is worth mentioning that until now, to calculate MRT, we have to use different software and algorithms to determine the different parameters of MRT, and this process can be very time-consuming. During this presentation, I'm going to show you the process that how we gather all of these radiations from the environment and how we can analyze surface temperatures and radiation from them, atmospheric radiation, direct and diffuse solar radiation, and more importantly, how we should manage to find all these data for every single point based on the geometrical view factors. So if you imagine a person fully exposed to the environment, basically we can calculate the mean radiant temperature based on this formula, which includes three parts: radiation from sun, from sky, or atmosphere and urban surfaces. By going into each parameter and introducing it, I'm going to simply explain all the required variables to calculate the mean radiant temperature and also some challenges that we had to solve to accelerate the entire process. The first variable is the Boltzmann constant. Boltzmann showed that there is a direct relation between surface temperature in Kelvin to the fourth power with radiation from that surface. This is for a black body, and for a gray body, we need to add emissivity, which depends on the material properties. By changing the equation, we see where the main formula came from. Thus, the first part is about sun radiation, and the first variable is the human body absorption coefficient, which varies based on the skin color, amount of water in our body, and so on. In general, it is assumed 0.7 for the short-wave radiation. The next one is solar radiation, including direct and indirect solar radiation and the diffuse sky radiation. The last one is the sun view factor, how the sun can see us, which depends on the sun altitude and azimuth, body area, and person body position. The sun view factor can be calculated based on this formula, but later I explain how we managed to calculate it to the unified process. The second part is about sky and atmospheric radiation. The first variable is the sky emissivity, which we can determine it from the formula by replacing the air temperature, dew point temperature, and sky cloudiness. The second one is the atmospheric radiation, that we can get it from this formula, which has different variables. We got the sky emissivity, Stefan-Boltzmann constant, and dry bulb temperature from the weather data. The next one is the sky view factor. If we project all the surrounding geometries to an imaginary hemisphere and then project it to the ground, by dividing the area of the sky to the area of the circle, we can define the sky view factor. I elucidate this part later to show how we manage to calculate it in our unified evaluation process. The last part is about the urban surfaces radiation. The first variable is the emissivity, which we can find it from surfaces properties, tables, charts. The second one is the long-wave radiation from surfaces, which is based on their last layer temperature. We use the Stefan-Boltzmann again, which we know, and it's the formula to get it. First is the Boltzmann constant. Second is the emissivity from materials properties. And the last is the surface temperature. To calculate the surface temperature, we need to solve the heat balance equation by knowing the indoor and outdoor temperature, the radiations that come to the surface, and so on. Then, by simplifying the equation, we can get the surface temperature. The last variable of the third part is the view factor. The view factor between the urban surfaces and a person's body. The view factor is the proportion of the radiation that leaves surface A and strikes surface B. So if you imagine two spheres with R1 and R2 as the radiuses and S as the distance, in this very simple condition we need to use this equation to calculate the view factor. Therefore, it's a very complicated factor and needs to be carefully calculated for different conditions depending on the surfaces and the body locations. In another way, Nusselt showed us if we mathematically project a surface to a hemisphere and then project it to the xy plane, the proportion of the projected surface area to the circle area can give us the view factor of A to B. In this regard, we started to distribute numerous points equally on the sphere with the potential to increase the number of points when it is needed. Assuming each point as a vector, and by extending these vectors, we can then define which of them can heat the surface, and by increasing the amount of the vectors, we can have a better projected image of the imaginary surface on our sphere by assigning a differential area to each vector. Therefore, with this method, we can project even very complex geometries to the sphere. This is a comparison study of the numerous vector method and the graphs that were calculated with a proved method before, and the studies shows similar results. Another comparison shows similar results, and also it illustrates the convergence that how increasing the number of vectors leads to a more accurate result. So far, we have solved the issues regarding the urban view factor section. Now, what about the previous challenges like the sky view factor? How can we use the same method to determine the sky view factor? If we assign a differential area to each vector and then project it to the xy plane, then we can calculate the sky view factor based on the numerous vector method by applying this formula. The next challenge is about the sun view factor. To analyze the solar radiation, we accumulate the radiation from each sky patch exposed to each point of interest. Hence, to use the numerous vector method, we need to assign a radiation value to each vector by the mean-weighted method. Finally, our challenges are solved, and we can calculate MRT with a unified evaluation method which accelerates the process dramatically. In summary, the process starts with shooting the vectors similar to the backward ray tracing process. If the vector heats the surface, we need to gather the surface properties and information and calculate the reflected ray. The surface radiation result goes to the total MRT, and the reflected ray goes back to the starting point. If it doesn't heat the geometry, we need to find the assigned sky patch, which shows the radiation from that direction, and the vector without any bounces is counted for the sky view factor and atmospheric radiation, and we need to gather all of the radiation's flux to the total MRT, the radiations from sun, sky, and urban surfaces. This is a very simple example of a courtyard that illustrates how by calculating the solar radiation, sky view factor, and surfaces radiations we can calculate the MRT for every single point. And for the assessment of the MRT in a more complex geometry, The same method is applied to calculate MRT for any time of the year. Thank you so much for your interest and attention. I sincerely appreciate that I've had this opportunity to present to you. Please let us know if you have any questions or comments. Thank you.